Accuracy is defined as a total number of correct predictions made by the model out of all the predictions. In the numerator, true positives and true negatives are our correct predictions. And all the predictions made by the algorithm, the right as well as the wrong ones, are in the denominator. So how would we know when to use accuracy? Accuracy is a good measure when the target variable classes in the data are nearly balanced. Let's learn about these with the help of an example. 60% of classes in our fruit images data are apples and 40% are oranges. A model that correctly predicts whether a new image is an apple or an orange 97% of the time is a very good measure in this example. So, when do we not use accuracy? Accuracy should never be used as a measure when the target variable classes in the data are a majority of one class. Let's go back to our cancer detection scenario where 5 out of 100 people have cancer. Let's say our model is very bad and predicts every case as no cancer. In doing so, it has classified those 95 non-cancer patients correctly and 5 cancerous patients as non-cancerous. Now, even though the model is terrible at predicted cancer, the accuracy of the model is still 95%. Precision refers to the closeness of two or more measurements to each other. It aims to answer the question, what proportion of positive identifications was actually correct? To explain precision in AI, let's use the same confusion matrix that we used for the cancer detection example. Precision is a measure that tells you what proportion of patients that are diagnosed as having cancer actually had cancer. The predictive positives were people predicted as cancerous, true positives and false positives, and the people actually having cancer are true positives. For example, consider the previously discussed scenario where only 5 out of 100 people have cancer. Let's say our model is very bad and predicts every case as cancer. As everyone has been predicted as having cancer, the denominator, true positives and false positives, is 100. And the numerator, which is the person having cancer and the model predicting as cancer, is 5. So, in this example, we can say that the precision of the model is 5%. Recaller sensitivity measures the proportion of actual positives that are correctly identified. Recall is a measure that tells us what proportion of patients that actually had cancer was diagnosed by the algorithm as having cancer. The actual positives, which are people having cancer, are true positives and false negatives, and the people diagnosed by the model as having cancer are true positives. Note that false negatives is included because the person actually had cancer even though the model predicted otherwise. Let's go back to our example of 5 out of 100 people who have cancer. Let's say that the model predicts every case as cancer. So our denominator, true positives and false negatives, is 5. And the numerator, which is the person having cancer, and the model predicted the case as cancer, is also 5, as the model predicted 5 cancer cases correctly. So, in this example, we can say that the recall of the model is 100%. And the precision of the model, as we saw earlier, is 5%. Now that we understand how precision and recall work, how do we determine when to use precision and when to use recall? It is clear that recall gives us information about classifiers' performance with respect to false negatives, while precision gives us information about its performance with respect to false positives. If we manage to capture only one cancer case and would capture it correctly, then we are 100% precise. Whereas recall is not so much about capturing cases correctly, but more about capturing all cases that have cancer with the answer as cancer. So if we simply say every case as cancer, we have 100% recall. This means that if we want to focus on minimizing false negatives, we would want our recall to be as close to 100% as possible without precision being too bad. And if we want to focus on minimizing false positives, our focus should be to make precision as close to 100% as possible. Specificity. Specificity is the measure of the proportion of the actual negatives that are identified correctly. It tries to identify the probability of a negative test result given a negative example. So, specificity is a measure that tells us what proportion of patients that did not have cancer were predicted by the model as non-cancerous. The actual negatives, which are people actually not having cancer, are false positives and true negatives. And the people diagnosed by us not having cancer are true negatives. Here, you should take a note that false positives is included because the person did not have cancer even though the model predicted otherwise. You might notice that specificity is the exact opposite of recall. Let's go back to our scenario of 100 people, out of which 5 have cancer. Let's say that the model predicts every case as cancer. So our denominator, which is false positives and true negatives, is 95. And the numerator, which is the person not having cancer and the model predicted his case as no cancer, is 0, as we predicted every case as cancer. So in this example, we can see that the specificity of the model is 0%. F1 score. Now that we have learned about both precision and recall, we realize that we don't want to carry both precision and recall in our pockets each time we make a model for solving a classification problem. To avoid taking both precision and recall, it's best to get a single score that represents both precision and recall, known as F1 score. Let's proceed to learn how to calculate F1 score. One of the easiest ways to calculate F1 score is to take the arithmetic mean, which is P plus R by 2, where P is precision and R is recall. But that's pretty bad in some situations. Let's take an example of fraud detection. Suppose we have 100 credit card transactions, of which 97 are legit and 3 are fraud. And we come up with a model that predicts everything as fraud.